Hello, everyone. It's 1 p.m. Eastern Time, and we're going to start the fifth week of the MTV Nuclear Engineering Summer School. I'm Flynn. I'll be moderating today for Dr. Sean Clark. He is a distinguished research scientist at the University of Michigan, works closely with Professor Sarah Pozzi, and he will be talking today about an introduction to the Monte Carlo and Monte Carlo methods. Please take it away, Sean.
Great, thanks, Flynn. Okay, hi everyone. I am happy to be here today to talk to you about the Monte Carlo method. So we're going to be talking about Monte Carlo all week. So my goal today is to give you all an introduction to the method, talk about a little bit of the history, cover some of the basic principles that underlie any kind of Monte Carlo calculation, and then I'm going to go through a number of examples to help drive those principles home. So there's a Q&A feature that we can use in the chat, much like any previous week. So if you do have questions during the lecture, please drop them in the Q&A, and I'll make sure there's plenty of time to answer those questions at the end. So what is the Monte Carlo method? It takes its origins back to the Manhattan Project here in the United States, which happened in the mid-40s. And its origin really comes from this notion of performing calculations on what was then the most powerful computer in the world. In fact, there's a little photograph of it there in the top right of the slide. It was called ENIAC. I forget what the acronym stands for, but it was essentially a numerical integrator. That was the first electronic computer, and you can see some of the stats there above the picture. It weighed 27 tons, it took up 1,800 square feet, used 150 kilowatts of power, and it was around 2,000 times less powerful than the phone that you have in your pocket. But nonetheless, it was the most powerful computer of the day, and it was suggested during the Manhattan Project that this computer could be used for calculations to support that effort. Specifically, Stan Ulam, who you can see pictured in the bottom left there of the slide, suggested using this machine for what he called a method of statistical trials. And this was kind of the first notion of what we know today as the Monte Carlo method. In fact, the three gentlemen you see at the bottom of the slide there are widely considered to be kind of the fathers of this method. Nick Metropolis in the middle was the one who first suggested the name Monte Carlo as the name for this method, and we'll kind of get into why that is. And then John von Neumann, who is at the far right, was the one who developed the first computer code to perform these calculations. So that's a bit of the history of how it sort of came about, but what is the Monte Carlo method at its essence? In fact, it's quite difficult to find a definition of Monte Carlo. If you Google it or try and look it up, you'll get a bunch of subtly different definitions, and there's several here listed on the slide. I'm not gonna read through them all, but you can kind of scan them visually and see some of the common themes popping out. These themes of random numbers or mathematical problems, numerical analysis, things like that. It's a solution method that we can use that is somehow based on random numbers. So it's a little bit confusing. How can we use random numbers to predict something that is real and physical? But that is precisely what the Monte Carlo method does. Random numbers are at the core of any Monte Carlo calculation. In order to perform Monte Carlo, we need a series, a set of accessible random numbers. And this notion is sort of where the name Monte Carlo comes from. It's a famous city that's known for its casinos and gambling. And that's why the term Monte Carlo was sort of associated with this technique, which is based on quote unquote rolling dice or randomness in some sense. So we use these random numbers in the Monte Carlo method to what's called statistically sample physical quantities from appropriate distributions. So the second bullet there is a lot of words that doesn't really say anything. It's really vague, but that is the essence of the Monte Carlo method. You have some physical distribution from which you want to sample for whatever reason. You want to sample from that distribution, and you do it using random numbers. And this is what we do in Monte Carlo. And doing this, if you do this a large number of times, you can produce a reliable statistical approximation of those quantities. Furthermore, the uncertainty on those estimates can also be estimated using Monte Carlo. So it provides not only a physical estimate, but also an associated statistical uncertainty. So we've talked about random numbers a little bit, but in fact, when we do Monte Carlo in practice, we don't use truly random numbers. In fact, truly random numbers are difficult to access. What we use are something called pseudo-random numbers. And the definition there is listed in the top bullet. It's a sequence of numbers that's distributed on 0, 1, so they're normalized. But the key is they're produced not truly randomly, but they're produced using a mathematical algorithm. So there's an algorithm under the hood that produces these strings of numbers that are, for all intents and purposes, random. There's existing several statistical checks that one can do to assess how random are these random numbers that these algorithms are producing. But suffice to say, they are sufficiently random. They can produce very large strings of random numbers on the order of 10 to the 20 or even more. Random numbers can be produced using these algorithms. They're generally recursive algorithms, which means each random number in the string has some dependence on the previous random number, which is by the nature of the fact that it's an algorithm. So they're not truly random in that sense, but they're random enough is a good way to think about it. What are the required properties of these pseudo-random numbers? So I already mentioned they need to be evenly distributed on 0, 1, meaning any number in that range is equally probable, right? Evenly distributed between 0 and 1. They should be produced speedily. When you're performing Monte Carlo calculation on a large scale, you can use millions of random numbers to do these calculations. So it is important that whatever algorithm is used to produce these numbers is fast and efficient. The third property is they should be reproducible. And this is important. This is a bit counterintuitive, but it's important for things like debugging. So if you're writing a Monte Carlo code and you're trying to solve a problem, in order to verify that it's working, you have to be able to have a reproducible result. So given a fixed starting number, which is referred to as the seed, given a fixed seed, the entire random number string will be reproducible. It'll be identical for the same starting seed. And again, that's purely based on the fact that they're produced with an algorithm. And the fourth property there is having a long cycle length, which means eventually these algorithms will repeat themselves. So they'll make a certain number of randoms, and eventually you will get back to the starting point. This is called the cycle length. And again, for these algorithms, that can be on the order of 10 to the 20 or even more. Okay. So that's our random numbers. That's how we get them. There's several ways to get them. MATLAB, Python, even Excel has its own number generator that we can use to make these. So random numbers are the first piece of Monte Carlo. The second piece of Monte Carlo is what's called the central limit theorem. So essentially what this theorem states is that a sample mean will asymptotically approach a normal distribution. So if you sample from a distribution long enough, the distribution of those samples will be normal, which allows the Monte Carlo method to be used to do these statistical approximations. Because we know that given a large number of trials, that distribution will converge to a normal distribution, we can predict not only the mean of the distribution from which we're sampling, but also the statistical reliability of that sampled mean. All right, so random numbers, central limit theorem, and then the next important piece of vocabulary here are what are called probability density functions. So a few slides back, I said that Monte Carlo is used to sample physical quantities from appropriate distributions. Okay, so now we're on to the appropriate distributions. These are things called probability density functions. They're written simply. If you go to a textbook, you'll often see them written as just P of X, which stands for it's a probability density function. And this P of X is a distribution that, for whatever reason, physics or otherwise, governs the parameter X from which we wish to sample. Okay, and you can see on the second bullet there what a P of X means. So P of X has to have two properties. The first property is it has to be normalized over the entire domain. So this integral from 0 to infinity has to equal 1, meaning that it's a probability something must happen. So this PDF has to integrate to 1 over the entire domain, whether it's an X domain or angle or energy, whatever it is. Over that entire domain, the integral must come to 1, meaning something must happen. The other key property of a PDF is that it must be positive definite. Again, probability, so it must be positive definite and integrate to 1. So that's our P of X dx. The second piece that we need to do Monte Carlo is something called a CDF, or cumulative density function. You can see in the third bullet there. This is often written somewhat confusingly as capital P of X. So lowercase p of X here is your probability density function. Uppercase P of X is how the cumulative density function is typically written. And the CDF is a derived quantity from the PDF. So to get a CDF, all one needs to do is perform a cumulative integral over the PDF to some value X. So because the P of X integrates to 1, this P of X is cumulative. So if you integrate over all values of X, this P of X would return 1 because you're doing a cumulative integral over the entire probability space. So if we have a PDF, we have a CDF, how do we actually do Monte Carlo based on that? So this slide really is the nuts and bolts of how Monte Carlo gets done. So again, if we remember that our capital P of X, CDF, is our cumulative density function, that means it takes values from 0 to 1. So what we can do is sample our random numbers, which conveniently, but not coincidentally, are also bound to 0, 1. We can equate those two things. So the CDF has integral limits of 0 to x. So this function here, integral 0 to x, P of x prime dx prime, this is a function of x because our upper bound is x, and it's set to a random number, which is a value, a number that we get from random sampling. So if we equate those two things and solve for x, what that returns is our physical parameter x as a function of our sampled random number, in this case, c. So this function, again, assuming P of x is nice and easily integrable, you can do this analytically, and I'll show some examples here in the slides of how we can do this integration analytically and end up with a mathematical function that relates the physical value we want, x, to some random number, c, that we pull straight from our random number generator. This process of doing this integral analytically and solving for x, this is called the inverse transform method. So this is done when P of x is a nice function that we can integrate analytically. There are other approaches one can take if P of x is, say, not nice or not easily integrable. Rejection methods, you can do table lookup methods, all kinds of different approaches can be done. But this is the core. Setting your CDF equal to random number, solving for x. This is the process that we call random sampling. And this is what's done millions of times in any Monte Carlo code or calculation that you would be doing. So that's it. That's all really there is to the Monte Carlo method. It's a simple method in many ways, but complicated in many others. So I want to spend the next maybe 25 minutes or so going through a few examples that will illustrate these concepts in degrees of increasing complexity. So the first example is going to be rolling a standard 6-sided dice, what that looks like in if we kind of talk about it in Monte Carlo concepts, PDF and CDF concepts. How do we understand this, very simple example in terms of Monte Carlo hit or miss experiment, which is a classical Monte Carlo example that you can find in any textbook. And then we'll get to two examples that are a little bit more based in physics. One is penetration through shielding, and then we'll finish up talking about the neutron random walk to really bring it back to the nuclear applications. Okay, so rolling a dice. I assume all 100 and some odd people that are on the call have at least at some point in your life rolled a die or a dice. In this case, we're going to talk about a regular single six-sided die. So when I say a die or a dice in this example, I mean a six-sided die. Furthermore, I mean a fair six-sided die, which means all six sides are equally probable. Okay, so if I were to task you for computing the average outcome for rolling a six-sided fair die, you could compute that. It could be computed a couple different ways. One way is you could do an experiment. You could get a single six-sided dice or a whole bucket of six-sided dice, throw them all on the table, record all the outcomes, and compute the average. Okay, this can be done. It's not exactly the most efficient way, but it can be done. And if you do this, you would return the average outcome of a roll of a single six-sided dice is 3.5. So you could do this experimentally, but what we're going to think about is how can we do this using Monte Carlo. So if now I'm tasking you to compute this average, but not by rolling the dice, by computing it using Monte Carlo. To do that, what the first thing you need to do is simulate the outcomes of rolling these dice, not by physically rolling them, but by using random sampling. Okay, so again, if we want to do random sampling, we need two things. We need a PDF and we need a CDF. This dice example is a certain situation where the probabilities are discrete. Okay, so it's not a continuous function in this case, it's a discrete function. We have 6 unique discrete outcomes. If we roll this six-sided dice, the outcomes are going to be 1, 2, 3, 4, 5, or 6. Okay, so our P of X is going to be the outcome of any single side. Okay, so if it's a fair six-sided dice, the probability of each of the 6 sides is equal, and it's equal to the value of 1/6. So our P of X dx is a simple constant equal to 1/6. Every outcome is equally probable. So if you want to compute the CDF from that, it's as written a few slides back, it's a cumulative integral. In this case, because our distribution is discrete, it becomes a cumulative sum. So again, capital P is what we use to denote our CDF, cumulative density function. And it's just a running sum. So the probability that our outcome is less than or equal to the ith outcome is equal to the sum from 1 to I. Okay, so it's a little bit confusing written in this arithmetic way, at least for me. I like to look at pictures. This is how the CDF looks like pictorially. Okay, so the probability that we roll the dice and we get 1 is 1/6. The probability that we roll the dice and we get 1 or 2 is 2/6 or 1/3. Probability that we get 1 or 2 or 3 is half, so on and so forth. The probability of getting any outcome, 1, 2, 3, 4, 5, or 6, is 100%. Something must happen. Okay, this means that our PDF and therefore our CDF were normalized appropriately. Oops. So given our CDF, this is how we can now do our random sampling. So if we wanted to sample a specific outcome for rolling these dice, what would we do? We would grab random numbers from a random number generator at MATLAB, Excel, whatever you want to use, Python. Ask for a random number, and it's going to spit back to you a number between 0 and 1. And if so you call the random number and you see where in the CDF the random number lands. So let's say you ask for a random number and it gives you a random number of 0.4. You would go along your CDF and you would find 0.4 lands in this band, which corresponds to an outcome on the dice of 3. You can ask for another random number, and let's say in this case, it returns a value of 0.7. So that would put you up here on your CDF, and that would return a dice value of 5. So this is how you could do random sampling of the outcomes for rolling six-sided fair dice using random sampling. So you could make a simple loop where you call random numbers however many times you want and link those randoms to outcomes on the six-sided dice and compute the average from your Monte Carlo sampled values rather than the values you would get by simply rolling a bucket of dice. Okay, example 2. So this is what's known as the hit or miss experiment. So again, you could find this in a lot of Monte Carlo textbooks. I have some references at the very end of the slide for some textbooks that I like. But in this problem, it's a thought experiment where we are trying to determine the area of some surface S. Okay, so you can imagine this surface S is some elaborate surface that we can't simply compute the area of. It's not like a circle. It's some elaborate surface that doesn't have a nice equation for it. So the question is, how can we compute the area of S? So if you think about this situation, imagine S, this surface of an unknown area, is bounded by a surface of known area. So in this case, we're going to consider this surface S to be bounded by a box. And this box has side length AB on the x-axis and CD on the y-axis. We can very easily compute the area of the square that bounds our unknown area S. So in terms of the thought experiment, if we had the area S laid out in front of us and we had that bounded by this nice square around it, and we started throwing darts or arrows at this combined set of surfaces, some of those darts would hit S and some of them would not hit S, right? Some of them would land in this green shaded region. Some of them would land in this purple region around the outside. And if we wanted to know then the area of S as a function of the number of darts which hit S, we can compute that as the ratio. Okay, so if we know the area of the rectangle, which is just base minus height, if we take that area, that known area, times the ratio of the number of darts that hit S divided by the total number we threw, that product will give us an estimate of the area of the surface S. So how do we do this using random sampling? So to use random sampling, again, we need a PDF, we need a CDF, and we have to do our inverse transform method. We're thinking about this problem in two-dimensional space. Okay, so our surface S was in the XY plane. So in order to simulate positions where our thrown darts would land, we need to generate pairs of pairs of values that correspond to XY coordinates. So we, in this case, need two PDFs, one for X and one for Y, both of our variables in two-dimensional space. Because we assume that we're going to throw these darts randomly, that PDF is going to be uniform in X and also uniform in Y. I'm showing here the calculation for X, but the calculation for Y is much the same. Because we're assuming these dart positions are random, we assume or we postulate that our X distribution is uniform, meaning each X value is equally probable. So our P of X dx is just some constant times dx. X is positive, that's fine, but this PDF on the first line here is not normalized. So we have to normalize it over our region of space. So the integral ranges here are A, B. If I just flick back, A, B were the bounds of our X variable, C, D were the bounds of the Y variable. So if we want to normalize this PDF, what that means is the integral over the entire range, in this case A to B, of our PDF, C dx, has to equal 1. So this is our normalization criteria. If we evaluate this integral and solve for C, that means that in order for this PDF to be normalized, the value of the constant C is 1 over the difference B minus A. So plug that back in for C, and then we need to compute our CDF, cumulative density function, that we're going to use to perform our random sampling. Okay, so again, CDF is the cumulative integral of our PDF. Our constant is 1 over b minus a, d of x prime. And we're going to integrate, not from 0, because our minimum value in this problem is a. So from our minimum value, which is a, up to x. Okay, so if you solve this integral and then invert it to solve for x as a function of c, you're going to get this expression down here. Okay, so this is a really long way to essentially derive linear interpolation. Okay, so our values of x take a minimum of a. So if our c value is 0 here, x is a. If c value is 1, because remember, random numbers are ranging from 0 to 1. If c is 0, x comes to a. If c is 1, x comes out to b. So this first line here will indeed produce x coordinates that are uniformly ranging from a to b. For the y coordinate, it's much the same. Everything is the same, only our y variable is ranging from c to d rather than a to b. So these constants just come out a little bit differently. The important bit here is that to produce the y coordinate, we have to sample a second random number. Okay, so these two coordinates must each be sampled using their own random number because they're independent of one another. Okay, so we're assuming that if you're throwing these darts truly randomly, the x position of a throw has no dependence on the y position of that throw. So by grabbing pairs of random numbers, c and eta, we can return pairs of coordinates x and y. So comments, again, for this type of experiment to be valid, these positions must be chosen uniformly over the entire rectangle, which means you don't want to bias your sample. In order for that ratio of n over n to be representative of the area of S, you have to fully cover the space of the rectangle, which is handled by the fact that our random numbers are ranging from 0 to 1, and we use a CDF. So this is fine. And again, as I just said, the x and y values must be independent of one another from a constant PDF. Okay, so this hit or miss experiment seems a little bit academic, but it's actually the same algorithm that's used for something called rejection sampling. So in Monte Carlo calculation, if you're trying to sample a variable that you don't really have an expression for, but you know how it behaves, you can do this type of calculation to do a rejection sampling and accept only values that land in a certain region of space, energy, time, etc. Okay, now let's talk about physics. So this third example is penetration through shielding material. So this is a problem where we're going to think about a block of shielding material that is relatively thick, and we want to calculate the probability that a single particle, makes it through that block. This problem is defined in such a way that that calculation can be done analytically very easily. I'll show on the next slide. But we want to compute it using Monte Carlo. And in fact, in this case, we can do something a little bit more clever where instead of using random number generator or pseudo-random numbers from a code, we can compute this probability purely using dice. So instead of using a random number generator from a MATLAB or Python, whatever, we can use dice to generate our random numbers and do the sampling in that way. So the calculation here is for a shielding slab that is 4 half layers thick. What a half layer means is that every time a particle passes through a single half layer, there's a 50% chance the particle will actually make it through. Half the particles will be absorbed in each layer is another way to think about it. So if we have a slab that's 4 half layers thick, the probability that a single particle will make it through is 1 over 2 at 1/2 to the 4th, because there's 4 half layers, which is equal to 1 over 16. 1/2 times 1/2 times 1/2 times 1/2, 1 over 16, which is around 6%. So we've already solved this problem. We don't need to use Monte Carlo, but we can. Okay, we can, and we can do it in a way that is involving sampling using dice rather than random numbers, which I think is pretty cool. So in this case, what we want to do is figure out if particles passing through every half layer will be absorbed or not. So in this case, we can set up a relatively simple CDF, which states that if we roll a dice for every particle, values of 1, 2, or 3 would mean the particle did not make it through that slab, or the particle is being absorbed. And other outcomes, 4, 5, and 6, would mean the particle does indeed make it through the slab. So we could start with however many particles that we want to start with, and we could roll these dice and figure out how many particles make it through the slab. And that would give us not only an estimate of our outcome that we already know, it's 1/16, but we can, if we do this now a number of times, we can predict that outcome, 1/16, as well as the associated uncertainty, which is a function of the number of particles that make it through that slab. So this is an example of how we do that. So in this problem, if you were to start with only 16 particles on the front of the slab, you would expect one particle to make it through out of those 16 on average. Now, Monte Carlo is a random stochastic process. So if you begin this calculation with only 16 particles, it's likely that 0 or more than 1 will make it through. But regardless, the error on that calculation is proportional to 1 over the square root of the number of particles that make it through this slab. So by starting with only a few number of particles, we can only expect a few number of scores at the end. So if we were to start with 100 particles instead of only 16, we'd expect a handful to make it through, 5 or 6 to make it through after the sampling. So we would have the same estimate of the mean, but with a reduced uncertainty. So this is a way that we can estimate the uncertainty for Monte Carlo, but it also shows how we need a large number of scores or a large number of trials to really converge to an accurate or precise estimate of whatever it is we're trying to calculate. In this case, we're trying to calculate a transmission probability that we know to be 6%. But if we do it with sufficiently small number of particles, we will have a large uncertainty on that estimate. In fact, if I just go back again, I'm a pictures person. If we start the calculation with only 16 particles and we get lucky enough that one of them makes it through, as drawn here on the picture, our estimate would be 1/16, which is the correct value, but the uncertainty on this would be 1 over the square root of 1, which is 100%. So we need multiple particles to make it through to reduce this uncertainty. If we started with 32 particles and 2 made it through, the uncertainty would be 1/√2 instead of 1/√1. So while we get the same mean, we're reducing the uncertainty. So we can do this a couple of ways in Monte Carlo. You can just simply use brute force, which means you just start with more particles. If you start with more particles, you're going to end with more particles. That's just the way it works. But there are kind of more clever things you can do with Monte Carlo, where you can do something called particle splitting, which is you can split particles in different regions of the problem. So this slide could be an entire lecture in and of itself. But I'll just touch on it because it's kind of interesting. What we could do is, because we know the transmission probability of each layer is 1/2, what we could do is every time a particle made it through those boundaries, we could then split those particles once they cross the boundary. So at every boundary, half our particles get absorbed, but then we split them into 2, so we then recover the particles that were absorbed in the previous layer. To do that, we have to adjust something called the weight. So one cool thing about Monte Carlo is that the quantities you're sampling can be sampled from any PDF you want. But if you want to relate your Monte Carlo sampled quantity to a physical value, you need those PDFs to be physical. But we can make adjustments to those PDFs and then adjust particle properties accordingly. And one particle is called the weight. So in this case, if we know we split the particles into 2, we then just score those particles with weight equal to 1/2. So that just results in this extra splitting factor on our estimate and allows us to produce an increased number of scores for the same amount of starting particles. This is something called variance reduction that allows us to reduce the variance of a Monte Carlo calculation for the same number of starting particles. Okay, again, this could be an entire lecture in and of itself, but there are many ways that one can do this, not just by particle splitting, but you can also just simply change the way particles get sampled in the code. And as long as you correct for it when you do the calculations, everything comes out okay. And this is how we can make Monte Carlo calculations to be very efficient. Okay, so I've got about 15 minutes left, and I want to talk a little bit more about some nuclear applications here. So I want to talk about neutrons and how we can use Monte Carlo to sample neutrons as they're going through a slab. So the previous example was this fictitious particle that got absorbed half the time. In this case, we're going to talk directly about neutron physics and how we can use Monte Carlo to sample physical properties of neutrons. Okay, so we're going to set up a toy problem here with a couple of simplifying assumptions to make our life a little bit easier for our 15-minute discussion here. We're going to assume we have neutrons coming into a slab, and this slab is a fixed thickness d, and we're going to assume it's just one-dimensional. We're not going to play with the other dimensions just for simplicity's sake. So it's a simple slab, and it only has two possible interactions for the neutrons. And we talked about cross sections and physics a few weeks ago in the summer school. But in this case, we're going to assume that these neutrons can do two things in the slab. They can either scatter or they can get absorbed. We're not going to have any fission, nothing like that. If they get absorbed, they're just absorbed. If they scatter, they're going to change their direction. But we're going to make a gross assumption that these neutrons don't lose any energy when they scatter. Okay, we're just going to concern ourselves here with the simulation of direction and figure out how these neutrons walk their way through the slab. And making this assumption allows us to do this problem with a constant cross-section. If neutrons change energy, you have to change the cross-section, and that just adds another level of complexity. So in this case, we're only going to concern ourselves with, from a directional standpoint, how neutrons kind of meander their way through this slab of thickness d. So if this was our situation, these neutrons can only have one of three things happen to them. They can get absorbed, which means they don't make it out of the slab at all. They can transmit, they can fully make their way through the slab, or they can reflect, meaning they can bounce back through the front of the slab through which they entered. So visually, it looks like this. If our neutrons are coming in from the left here, they can have the green outcome where they kind of bounce around a few times and they transmit through the opposite edge of the slab. They can be absorbed somewhere in the slab, which means they never make it out, or they can be reflected. So how do we compute these probabilities? If we know the slab thickness and we know these cross sections, how can we compute these three probabilities: transmission probability, absorption probability, reflection probability? So we do that through this concept called the random walk. So random walk is a concept that's typically talked about in the context of neutron transport, just because of kind of how we drew it on the previous page. Neutrons just bounce around a lot, and they can be seen as having this random walk through the medium. Okay, and the nice thing about, or the neat thing about it, is each of these states within the random walk. So it's shown here on the left. Each state in the random walk is viewed as a collection of variables: position, energy, and direction. Each of these sets of state variables from one state to the next is random. And it's random in the ways I'm going to show on the next slide. So what we do is we can track the neutron at every state in its life and figure out at what point the neutron's life ends. Does it escape? Does it get absorbed? Etc. So at the beginning of the life, the neutron is going to be born with some properties, and some of those may be random, some may not be random. It depends on the source. But we can have a neutron source that's born at a certain position or some directions, energy. All these things could, in principle, be random. So we got to figure that out. Once the neutrons are born, they're going to travel some distance in the medium before they collide, and that is most definitely random and depends on the cross-section data in that medium. If the particle collides, it will scatter maybe, or it might get absorbed. But if it scatters, it's going to scatter in some direction. It could lose energy if we wanted to consider that, but for our example, we're just going to consider the direction. All of those things are random and they're all based on nuclear data. If the particle gets absorbed, maybe that makes extra gamma rays, or maybe it causes a fission. All of these particles are also random. So everything in this neutron's life is random, and that's how we think about this in terms of a random walk. So our question is, how do we simulate these individual processes? So the first thing the problem begins with is a particle source. So in our case, we're considering one dimension. So some of this gets a bit simplified, but in Monte Carlo calculation, what's typically done is the source properties are all sampled independently from one another. So the position properties of the source, the directional properties of the source, the energy properties of the source, these are generally assumed to be separable unless there's some very good reason why they're not separable. So we can consider each of these things to have their own PDFs from which we can sample the various properties. So in our case, in the simple problem, we just assume the source was placed just next to the slab there at the left. So the energy is fixed, position is fixed. So we only need to figure out what's the direction that those source particles are going to travel. Okay, so relative to our slab, which direction are those particles being emitted as they enter the slab? So in our case, for the source energy, we're essentially assuming it's monoenergetic because our calculation is only considering direction. But in real life, you may have, discrete energy sources of multiple energies. You can have continuous spectra. All these things have well understood PDFs that can be used for more complicated problems. So in our case, we're only considering direction. So we're running a little short on time here, but these probabilities can be calculated using CDF. So if we have a particle source that's placed just next to the slab and we want to sample the direction of that source isotropically, meaning every direction is equally probable, we can do so in this way. And the normalization gets done by setting up this P of omega d omega to be constant, again, meaning every direction in 4 pi is equally probable. And our normalization constant just comes out to 1 over 4 pi, which is the integral of solid angle over all space. So the write-up here is just how we could separate the solid angle omega into 2 different angles, theta and phi, and we can treat them separately because the azimuthal and polar angles are independent of one another. So in order to sample this direction fully, one needs to sample sets of random numbers. So much like we did the hit-miss problem where we had an x and a y coordinate, in this case, we're going to result in theta and phi coordinates, or mu and phi coordinates, that we can then translate into a full solid angle direction. Okay, so this is the derivation. You can have a look later if you'd like, but basically we're going to integrate this mu vector, which is cosine theta, from -1 to mu, where -1 is the minimum value of our cosine space. Set that equal to mu, and then for phi, it's going to be a constant distribution from 0 to phi. That's equal to eta, and we can sample those and figure out the different values for these 2 angles based on random numbers c and eta. So given those, we now know the direction. I think I was supposed to. Oh, that's what's happening. Sorry about that. The solution was hidden. You guys see this now?
We've got you back now. You're good.
Okay, cool, thanks. I thought something was missing. So here's the actual evaluation of these integrals. So if you set up the CDF in this way from -1 to mu, solve it with mu being cosine theta, you can sample values of mu as a function of c using this relationship, 2c minus 1. And then if you do the same thing for your phi variable, solve that, you can get phi as a 2 pi eta. So these expressions allow allow you to generate values of mu and phi as a function of c and eta, giving you the direction. Okay, now we're back on track. So we know the direction. The particle is going to leave the source, traveling in some direction. So the question becomes, now that it's in our slab, how far does it travel? This is something called distance to collision that gets done in every Monte Carlo calculation that you're going to do involving particle transport. And this is a function of the cross section in that material. So this big sigma is the sum of that scattering and absorption cross section I talked about a few slides back. And we can set up our PDF based on the known behavior. So this is an example where the value of the PDF comes from our knowledge of physics. So we know that the neutron transport in these slabs goes like e to the minus sigma r or x. Because we know this from physics, that allows us to set up the PDF to follow those known laws of physics. So the probability that a neutron will collide in r plus dr is equal to e to the minus sigma r dr. And this needs to be normalized again. So if we set up our same normalization criteria where the integral of this thing has to equal to 1 over all dimensions, we can figure out the constant has a value of sigma, which is total cross section. And then the random sampling can be done using the inverse transform method in the same way we've done it with the previous examples. So P of R is our CDF, cumulative density function for distance, integrated from 0 to r, e to the minus sigma r prime dr prime. We solve that integral, we get this, invert it, and then we wind up with this very nice expression of how we can sample the distance a neutron travels in a medium that's governed by total cross section, big sigma, as a function of our sampled random number. Okay, so we go to our random number generator, grab a random number, and based on the value of that number, that would tell us how far the neutron travels before it collides. And the last thing we need to ask ourselves is, when the neutron collides, what type of collision happens? So in our simple problem, we only have 2 possible outcomes. The neutron can either scatter or it can be absorbed. And this is a more general example where we can have many different interactions that occur. But this is a discrete PDF, much like the dice example we had from example 1. This is a discrete PDF representing all of the different possible interactions that a neutron can have in a medium. So in the dice example, back in the beginning of the lecture, we had our fair 6-sided dice, so all the sides are equal to 1/6. In this case, you could think of this as an unfair n-sided die. Okay, so it has many sides, and each side is not equally probable, but the theory is the same. Okay, so we can set up the PDF as the sum of the cross sections. We can normalize it by dividing by the total, and construct the similar step function, just like we did with the dice example. Okay, but again, these steps are going to all be different sizes based on the relative cross sections. So in our case, if we only have absorption and scattering cross section, we would just sum those two together and then sample random numbers and figure out is it greater than or less than the scattering and absorption cross section. So if the neutron were to get absorbed, that would give us the absorption probability. So that would end that track, start a new one. If the neutron gets scattered, we would have to go back and then sample the new direction of the scattered neutron using the same relationship as we have here. Scattered neutron is going to be isotropic, so it's going to go in a new direction. It's going to travel a new distance, and then if maybe it makes it out of the slab, maybe it gets absorbed, and we just do this in a loop until we determine the ending fate of that neutron. Okay, so we could do this as many times as we needed to populate our various scores of neutrons, making it through the slab, getting absorbed in the slab, bouncing out of the front face of the slab, and that would tell us the values of those probabilities that we talked about in the beginning of the example. Okay. So we would score these. In this case, we'd be scoring just the number of events. So we would just be looking at analog Monte Carlo, where we're just counting up the number of particles that get absorbed, counting up the number of particles that transmit through the slab, counting up the number of particles that get reflected back through the front of the slab. So this is what's known as analog Monte Carlo, where you're performing the random walks, you're doing the random sampling, but everything is analog. Every particle track is a real particle. The one slide where I talked about variance reduction, that gets you down into this realm of weighted Monte Carlo, where PDFs can be altered, to allow for more efficient scoring. Okay, so by just summing up all these different outcomes, we can then estimate these various probabilities. Okay. All right, this is my final slide. Just to talk again about Monte Carlo. Why do we use it? When is it used? So there's a number of advantages to Monte Carlo. It's efficient for multidimensional problems because you have all the random sampling capability. It allows you to represent complex geometries in a real way. So we don't need to do any homogenization. It's using full pointwise data. So we're not reliant on how well we can homogenize a certain region of our calculation. Whereas deterministic methods often require homogenization. Because of this, we can also use Monte Carlo as kind of an analog to a numerical experiment. So it's in many ways can serve as a nice way to validate deterministic codes, which often have assumptions such as energy groups or spatial homogenization, things like that. So it's very good. What are the downsides though? So it's not perfect. The biggest two biggest disadvantages that get cited for Monte Carlo is one, a large memory requirement. So because it uses pointwise data, which is an advantage, it can also be considered a disadvantage because whatever data that one needs, whether it's cross sections, angular distributions, whatever you need, temperature dependence becomes a real challenge. All those data have to be loaded into the memory so that the code can access them for all the sampling. So this can result in a large memory requirement. Thankfully, these days, memory is fairly inexpensive. The second one is potentially long runtime. So fundamentally, the statistical reliability of your calculation depends directly on the number of samples, the number of histories. So to get an accurate estimate, you need a large number of samples. So depending on how complex the problem is you're solving, it could take a long time to simulate all these samples. So, but again, computers nowadays are becoming more and more powerful. On my MacBook, I can run millions of histories per minute for a typical problem. So it's becoming more and more reasonable to solve standard problems using laptops. Now, if you're trying to use Monte Carlo to solve like a full nuclear reactor or something like that, then these challenges really do begin to show themselves because of the large data and geometry requirements for those types of applications. So this are a couple of books that I like here at the top. Carter and Cashwell is a seminal textbook from the 70s that is really covers a lot of the underlying stuff. Carlo-Clarke is a more recent textbook, and of course, I based this off some of my own notes as well. So with that, we've got about 10 minutes left, and I'd be happy to take any questions if anybody has them.
Thank you, Dr. Clarke. As a reminder, the Q&A is open if you'd like to ask any questions. I see one right now, but we have 7 minutes left, so we could probably take one or two more. The first one is asking, could you use simulations like the Monte Carlo method to estimate radiation dose?
Yeah, that's a very good question. So I didn't talk about it here. I focused more on the transport, but you can definitely use Monte Carlo to calculate dose. Fundamentally, dose is just a tally of energy deposition. So there are ways that, much like we track this neutron random walk, and we were considering only direction in this example here, but you can also compute the energy deposited at every step, whether it's neutrons or photons, and figure out from those energy depositions how much dose would be delivered to, whatever cell the particles are being transported through. In fact, Monte Carlo calculations are often used for dose calculations because, like the thick slab, very simple example I showed of the particles going through the thick slab, that's a very typical type of problem that gets looked at when you're considering dose, because when we're, as radiation workers, if we're designing a system where dose is involved, we want to heavily shield whatever it is we're concerned about, right? So this problem, this thick shielding or deep penetration problem, is kind of tailor made for Monte Carlo. So absolutely.
Thank you, Dr. Clark. We've got a couple more involved questions coming up. I think these will be probably the last two for the talk. But Mr. Bryant asks, have we considered the new NVIDIA GPU server for the next phase of Monte Carlo calculations? So using GPUs in order to carry out sort of Monte Carlo transport codes.
Yeah, this is another really good question. I think this is something I should probably add to my list of advantages here on the last slide, because Monte Carlo is inherently parallelizable, and it's also very kind of tailor-made really for GPUs, because it's mostly linear operations, which are things that GPUs do very efficiently. So again, because Monte Carlo is based on this notion of multiple or a large number of independent statistical trials, we can very reasonably sort of place those independent trials on multiple independent cores or independent GPUs, which can certainly speed up calculations far beyond what you can typically do on a standard like laptop processor, for example.
Thanks, Dr. Clark. The next one, oh, sorry, I think they removed their question actually. Oh, sorry, Courtney, that was moving on the fly. I missed it. Thanks. For Markov chain Monte Carlo, have you explored its use for diagnosis of nuclear materials life in the reactor?
Yeah, that's an interesting one. That's definitely outside of my realm of expertise. I know Monte Carlo calculations are used for all problems at various stages of nuclear reactor, whether it's dose or reactor physics or neutron kinematics. I imagine it's also used for material studies, but I can't, unfortunately, can't comment on that.
Yeah, thanks. Sorry, but we definitely have expertise in Markov Monte Carlo chain at Michigan. So if you want to email us, we can connect you with people more familiar with the topic. Let's see. So last question, I think. Is there any attempt to use physics-informed neural networks to improve the Monte Carlo performance?
Yeah, this is neural networks it's a hot topic right now, and people want to use it for everything. And you can definitely use it's kind of an advanced variance reduction technique where you really set up optimal parameter space for the Monte Carlo transport. And that historically has been done, I guess, manually would be the way to talk about it. But I know there are folks working on using neural networks to sort of optimize the variance reduction type parameters to ensure that the histories that are being tracked are the ones that are most relevant to the quantity you're trying to tally, right? So if you're trying to tally dose or energy in a certain region of space, how do you make sure your particles get there? So yeah, absolutely.
Thank you, Dr. Clark. And I see we have another question here, but we are just about out of time. So if you'd like to
Yeah,
email
this is
it,
a quick one. I can answer.
Oh,
I can
okay.
answer this
Sorry,
one. Last one. 2 minutes left. Yeah, it's OpenMC. Yeah, so OpenMC is an open source Monte Carlo code that you can find online. There was another one about OpenMC. Maybe it was the same question that got dismissed, but it was a question about OpenMC and oh, now it's back for K effective. Yeah, I'm not sure if it's the same person because the first one's anonymous, but the quantum effects, no, Monte Carlo doesn't really handle MCP, I should say, doesn't really handle that, but I'm sure there are Monte Carlo codes that do. There are open source Monte Carlo codes. OpenMC is one. GNet4 is another one. If you're interested in, so to say, more exotic physics, so things beyond your typical neutron, photon, electron transport, which are things like MCMP and OpenMC are really good at. GNet4 is going to be another open source option that could allow you to access some of these more exotic things like quantum effects. And in terms of K effective, most packaged Monte Carlo source codes, like again MCP, OpenMC, are going to have their own eigenvalue solver built in, which that's how K-effective gets done in Monte Carlo. It's an iterative eigenvalue calculation.
Thanks so much, Dr. Clarke. And that's all we have time for today. We really appreciate your lecture tomorrow. I will be talking about simulating radiation detectors, building off of the Monte Carlo concepts Dr. Clarke has described. We'll touch a little bit on JANT4, but it'll be mostly MCMP tomorrow. So I look forward to your detailed questions like you've had for Dr. Clarke. Thank you all, and we'll see you tomorrow.
Okay. Thanks, Lynn. Thanks, everyone. Bye.